This is part 4 of a series on gradient boosting method. In this video, we will look at the training and prediction process of GBM classification. This video was produced in Korean and translated into English, and my voice was generated through AI, text-to-speech. The training and prediction process of GBM classification is also similar to the GBM regression process. Let's take a look at the training process of GBM classification through a simple example. This example references the StatQuest YouTube video. The data in this example has 3 features, X, and 1 target class, Y. The target class Y consists of yes or no. This is for binary classification. Yes is defined as 1, and no is defined as 0. There are a total of 6 such data points. Step 1 makes an initial prediction. Initially, we use the probability that the target class is yes as an initial estimate. Let y hat be the probability that the target class Y is yes. 4 out of 6 target classes are yes. So the y hat is 0.67. Next, we use the y-hat to calculate the log odds value. The log odds is defined as f. The log odds is calculated using this formula. The initial log odds is 0.69. We looked at the log odds in detail in the logistic regression videos. Since y-hat is 0.67, which is close to 1, we initially assume that everyone will like troll 2. Classification requires these 2 initial values. We got the y-hat, and then we got the log odds f. In step 2, we calculate the residuals using the actual target class, y, and the predicted target class, y-hat. Let's take the first data point of the first round as an example. The target class for the first data point is yes. So, the actual target class Y value is 1. And the initial prediction is 0.67. So, the residual R for the first data point is 0.33. In this way we calculate the residuals for all data points. In step 3, we create a regression tree model and fit this model to the features X and the residuals R. We are doing classification. But since the residuals are real values, we need to use a regression tree. Let's assume the generated tree is as follows. For the first data point, the favorite color is blue, so we move to the right. And the age is 12, so we move to the right again. The residual of the first data point then belongs to the third leaf node. In this way, each leaf node contains the residuals. Now we calculate the leaf value of each leaf node. The leaf value is calculated using this formula. We'll take a closer look at this formula in the next video. And in this video we'll just use it. Let's use this formula to calculate the gamma of the third leaf node. This leaf node contains 3 residuals for 3 data points. The initial estimates are all 0.67. This leaf node contains 3 data points. So the denominator calculation is like this. And the numerator is the sum of the residuals. Adding up all of these residuals is like this. Then the leaf value comes out to 1.49. The second leaf node has a leaf value of -0.77. The first leaf node has a leaf value of -3.03. In this way, we calculate the gamma, which is the leaf value of every data point. The gamma of the first data point is 1.49, because it belongs to the third leaf node. And the gamma of the fourth data point is -3.03, because it belongs to the first leaf node. Step 4 updates the old prediction. With the new prediction. This is the new prediction, y hat, in the table below. The leaf value, gamma, was estimated in step 3. Step 4 uses this gamma value to estimate the log odds, f, and then uses this f to estimate the next predicted y hat. The process for estimating the log odds is as follows. Let's estimate the f value for the first data point. The formula for estimating f is like this. The log odds value from the previous round is f, m-1. Alpha is the learning rate, gamma is the leaf value, and I is the indicator function. J is the leaf node number. In this tree, j is from 1 to 3. The first data point belongs to the third leaf node. So the indicator function, I, is 1, only when j is 3. And all other I are 0. For the first data point, the log odds value from the previous round is 0.69. The learning rate is 0.8. And the leaf value gamma when j is 3 is 1.49. Therefore, the new log odds f value for the first data point is 1.88. Next, let's calculate the new log odds, f, for the second data point. The second data point belongs to the second leaf node. Therefore, the indicator function I is 1 only when j is 2. And all others are 0. The leaf value of the second leaf node is -0.77. For the second data point, since the log odds f of the previous round was also 0.69, and the gamma was -0.77, the new log odds is estimated to be 0.074. In this way, we estimate the new log odds for all data points. Next, we use this log odds to estimate the new y hat. This equation allows us to compute log odds f using y hat, while this equation allows us to compute y hat using log odds f. The log odds, f, of the first data point is 1.88, so the y hat is 0.87. And the y hat of the second data point is 0.52. In this way, we estimate a new y hat value for every data point. The new prediction will then be closer to the actual target y. The new y hat for the first data point is 0.87, which is closer to 1 than the initial prediction of 0.67. And the new y hat of the fourth data point is 0.15. Which is closer to 0 than the initial prediction of 0.67. And the fifth and sixth are also closer to 1 than the initial prediction. For the second data point, it was a little further from 1. But will get closer to 1 as the iteration progresses. Initially, the predictions for all data points were all the same, which was 0.67. So the residuals were this much. After one iteration, new predictions were updated with these values. And these residuals got smaller. Step 5 recalculates the residuals using the newly predicted y-hat. On the previous page we calculated the y-hat for the first round. Now we use the difference between the y-hat and the actual y values to calculate the new residuals. R. For the first data point, the actual y is yes, and the y-hat is 0.87. Since yes is 1, the residual is 0.13. And the residual of the second data point is 0.48. Step 6 generates another tree using the features x and the residuals r. Again, each leaf node in this tree contains the residuals. Then we calculate the leaf values in the same way as before. The third leaf node has the residuals from the data points 1, 4, 5, and 6. The leaf values are calculated like this. The y-hat of the first data point is 0.87. And the y-hat of the fourth data point is 0.15. And the y-hat of the fifth and sixth are both 0.87. And the sum of the residuals of the third leaf node is like this. Then, the leaf value will be 0.51. Therefore, the leaf values, gamma, of the data points belonging to the third leaf node are all 0.51. In this way we calculate the gamma for every data point. And in step 7, we calculate the logdds f and estimate the new y-hat, just like on the previous page. That is, we use the gamma to obtain the logdds f and use this f to estimate the new y-hat. This will update the predictions for all data points. The first data point is closer to the target class, yes. And the second is also closer to, yes. The third data point is closer to, no. As these iterations progress, you can see that the predictions become more and more accurate. Repeat this process until the residuals are sufficiently small. In classification, the y-hat is not predicted directly, but rather through the leaf value gamma and the logdds f. That is why the classification is more complex than regression. This time, let's look at the prediction process. We have test data as below. Our goal is to predict the target class for this test data. During the training process, we created and saved the two trees below. Let's input this test data into each tree. This test data point belongs to the third leaf node of the first tree. And it also belongs to the third leaf node in the second tree. Step 8 predicts the target class for this test data. First, we estimate the logdds f. F0 is the initial logdds value of the training data. This is 0.69. The learning rate alpha is 0.8. And when this test data is fed into the first tree, the leaf value is 1.49. And the leaf value of the second tree is 0.51. Therefore, the logdds f for this test data point is estimated to be 2.29. Now we use this value to predict the probability of y. This is the probability that the target class y is yes. This probability is 0.91. Since this value is greater than 0.5, the class for this test data is predicted to be yes. This is the prediction process. For simplicity, we only did 2 iterations. But in practice we just keep iterating until the residuals no longer decrease. If so, the leaf values will continue to be added like this. And since the residuals continue to get smaller, the values to be added will also get smaller. So far, we've looked at the training and prediction process for GBM classification through a simple example. In the next video, we will analyze the GBM classification algorithm in more detail.